as yesterday, I will invite to Jutta, Niels, and Miguel Alcubierre, if it's possible to answer for all of us this kind of question. Let me share my screen and can you see it?
Yeah.
Okay, so we have more or less 30 minutes and 3 questions. So I think 10 minutes for each question and 3 minutes per person and 2 minutes to comments or question, no? So my first question is kind of philosophical. So black holes really exist in nature or not? So Jutta, if you wanna start the
yes, I'll be happy to give my personal view, and I firmly believe black holes exist free in nature, I must say, even though I'm spending a lot of my time on looking at alternative objects like boson stars or others. But I think we have understood the evolution of stars quite well by now. And then we know that when the fuel is burnt up, there's just no internal pressure against gravity anymore. So collapse is going to happen. We see these supernovae. And then we have the end products, right? So what are these end products? Neutron stars, certainly. But when we have small enough masses of this remaining star, this center, this burnt out piece, because we firmly believe also we sufficiently understand neutron stars that there should be some upper limit. Of course, when we go to alternative theories of gravity, which I also like to go, we can increase this number somewhat, yes, but something is going to give them, right? At some point, the nuclear matter or whatever matter won't be able to work against gravity anymore. And I must say, thinking about Eddington and how Eddington was arguing that there should be some force in nature that would prevent such a thing like gravitational collapse. I don't think we have such a force. I firmly believe that the end product is going to be a black hole. So when we look at systems like the Cygnus X1 and its companion, I firmly believe that we do have a black hole there in this binary. And so there should be at least stellar black holes. And when we look at observations from gravitational waves, we also think, now with more recent ones like last year's, they could be intermediate mass black holes, right? 142 solar masses was one event. So yeah, probably also what we observe in the center of the galaxies are black holes. So from my point of view, I really believe black holes exist. Certainly below mass ones.
Thank you, Jutta. Niels, you want to add something?
Yeah, I mean, I guess kind of following that, I'd say we certainly have no observational evidence to the contrary. Black holes are simple objects that well fit the data. But we're moving into a different era. Previously we've had kind of weak field measurements, even strong field measurements, but now with gravitational wave detection, we have the first kind of fully dynamical spacetimes of binary black holes, and we see that this does match reasonably well the LIGO data or LIGO Virgo data. Of course, those measurements and the constraints they can put on at the moment are still reasonably weak. That they're still very impressive measurements, but they're talking about constraining certain parameterized post-Newtonian coefficients at quite a low level. So, constraining those coefficients at the sort of 1 or 10% level, worse depending on how high you go in the PN series. So, yes, I mean, I certainly believe they exist, and we certainly have no data to the contrary. I'm not an expert on alternative theories by any stretch of the imagination, but it always seems to me that it's extremely hard to construct another alternative theory. Like Einstein's theory does seem to be very simple and very elegant, and as soon as you try and disturb it, it becomes very difficult. Maybe that's telling us something, maybe not. Yeah, I think I would say this. I would also add, it's important to study these alternative theories because we need to go to particularly gravitational waves observations. We need to have models to compare against to check that whether or not our models well fit a theory that's different from general relativity. So models that maybe don't have black holes in, exotic compact objects or something like that. Because otherwise you run into a danger that, you've only got GR to test against, that you detect these things and you estimate their parameters, but there's a degeneracy with some non-GR theory. So it's crucial to also have models in the future, which is a much less developed area of modeling at the moment for beyond GR theories of gravity, and that will help us answer this question.
Thank you, Niels. Miguel, what do you think about it?
Yes, I completely agree. I think, as you just said, GR is a very simple theory, and black holes are inevitable in that theory. In fact, I'm not a person that does observations. I'm more of a numerical relativity person. But still, even though I'm not directly related with the observations, I think the observations already point to the fact that they do exist. I mean, we have a lot of evidence, and it's very difficult to construct something that looks like that, and it's not a black hole. So a lot of people are trying, and I think that's important, as Niels saying. It's important to check and to try to build alternatives. But at the moment, the simplest explanation is that these things are black holes, and they seem to fit all the observational parameters that we need. And also, on the other hand, since I'm a numerical person, when I do numerical calculations, getting a black hole is easy. Not getting a black hole is hard. I mean, anytime you do a numerical calculation in numerical relativity and you have some sort of matter, it wants to form a black hole, and it's the first thing it does. And it's not even a very difficult solution. I mean, the black hole solution is actually very smooth and very nice. I mean, you might worry about what happens at the singularity, and let about the people doing quantum gravity worry about that. Maybe the singularity itself doesn't exist, but the rest of the space-time, certainly the horizon region, that's actually a very smooth region, and it's a very natural solution of the equations. So if black holes don't exist, then the theory must be completely wrong, even the classical regime, and very, very wrong. It's not, I mean, black holes are not a very special solution. Actually, they're the natural solution. They happen all the time. So I think that if the theory is correct and the observations seem to point in that direction, then black holes, I think, are inevitable. And I think certainly they do exist in nature, and we have a lot of evidence about that today.
Thank you, Miguel. So I don't know if somebody want to add something to this discussion. I cannot see the chat, so Celia, maybe somebody asked in the chat.
No.
Cesar, I can see Cesar. Come on, Cesar. What do you think about it?
Yeah, turn on my camera, please. Sorry. Yeah, well, you really went philosophical into this one. And I believe that this whole question is entirely based upon our belief that the way we understand and model nature is actually indistinguishable from nature itself. So what my point is that general relativity, good as it is, extraordinary as it is, and as much as I love it, is not interchangeable with nature itself. That wouldn't make any sense to begin with. But it is indeed the best way of understanding nature. So in my view, asking if black holes really exist in nature is really a statement of belief in the ideas that you're trying to map to the real world. So it is indeed philosophical. And I do believe they exist.
Okay. Thank you. So I don't know if somebody has some comment.
Oh, I just wanted to add something. It depends
Yeah.
also on what you define by a black hole, right? Because the formal definition of a black hole that is in the textbooks, say Wald's textbooks, that black hole probably doesn't exist because it's eternal. And we know that eternal black holes don't exist. We know that there's Hawking radiation, so they should evaporate. And that means that there's no event horizon. So if you're talking about an event horizon as such, then probably they don't exist. But if you're talking about an apparent horizon, something, a trap surface, I'm pretty sure those do exist. I mean, that's extremely difficult to get rid of. So, yeah.
Okay. Thank you all. So let me go to the next question. So what's up? Okay, the next question is, what is the future in the study of compact objects and observation of the universe by using gravitational waves and so on? Jutta, do you want to start?
Thank you. Compact objects, this is a very wide subject, right? We I spoke a lot about those compact objects. I would say we know they exist, but I mean, this is now addressing also the last question, the neutron stars and the black holes, but there might be many different compact objects, right? So as compact objects, very compact objects with light rings, let's say, you would also have wormholes. They would qualify, or boson stars, or party-like solutions. There are lots of different possibilities. So in that sense, I think this is a very wide question. And now gravitational waves, of course, give us a lot of information on those objects that might be there. We don't know which of them are there. We know about, I think we know about neutron stars and black holes, but the others, they might also be there. We just don't have real evidence for them, but we studied them as contenders. And now I think with the current gravitational wave observations, we learn already quite a bit about them. However, the new generations of telescopes with the Einstein telescope or with LISA will have increased our knowledge in a tremendous way. So I think this is a really fascinating future because we're going to learn so much more about these objects, and then possibly, hopefully, also about alternative theories of gravity, because they might have different gravitational wave signals. So I just think gravitational waves in the future and compact objects, I'm completely optimistic. It's a wonderful time ahead of us.
Thank you, Jutta. Niels?
Yeah, I completely agree. I think it's a wonderful time ahead of us. And I think it's worth remembering that we really are at the very beginning of gravitational wave astronomy. It's been around for 5 years now. You know, we're back at the level, you know, compared to EM with Galileo of his telescope. We've made the first observations, but there's so much more that can be done. And the first observations, as wonderful as they are still imprecise. There's lots of issues to be dealt with. And I think, yeah, the point you mentioned about, you know, future detectors coming online, well, upgrade to the current detectors, certainly. You know, we're already seeing huge amounts of systems being detected. There's a lot to be done from astrophysics working at populations. But future detectors, I think, really hold a promise of testing GR at a much more precise level, just because you get stronger signals. And I mean, ground-based detectors, you know, Cosmic Explorer and Einstein Telescope and so on. But also, as mentioned, you know, the LISA detector offers an opportunity to explore different objects, ones of higher masses, typically involving massive black holes and lower frequency systems. And they are talking about signal to noise ratios, you know, not of 20 or 30, but of 500 or 1,000. So you get incredibly loud signals that really, if there isn't to be any deviation from GR, if it hasn't been detected at the ground, then that's when it might be detected there. So yeah, I think the future is really very bright for gravitational wave astronomy. Just in the first few years, it's already done so much. And I think there'll be a lot more to come and a lot more precision as we go forward in particular.
Thank you, Niels. Again?
Yeah, I agree with what Yuta and Niels just said. We're only beginning gravitational wave observations. We've only been getting them for 5 years, and we have about 50 or 60 detected systems. And with the current detectors, I think we won't be able to general relativity in great detail, but we will be able to do statistics of the formation of these objects, their parameters, their masses, the spins. So there's a lot of very interesting astrophysics we can do with this current generation. But if we want to test GR and alternative theories, we need to wait for the next generation of detectors that will have much higher sensitivity. For example, one thing that would be extremely interesting also, not only to check different theories of gravity, but also just to, for example, if we get more of these systems with neutron stars, that would be ideal, right? So even though I love black holes, if we get all these collisions of neutron stars, we should be able to start learning something about their structure and maybe even their equation of state. But we really can't do that with the current detectors. The sensitivity is not enough. With the next generation, I would hope that we should be able to, even within standard GR, to study the properties of neutron stars, maybe learn about their sizes, really their physical size, their spins, and with that constraint, the equations of state that people have been proposing. So we're only at the early stages. There's a lot of things to do. And I think things will change dramatically once we have the Einstein telescope and LISA, and we will be able to see so much more about the universe. So yeah, I think the future is really bright, and we are only just starting.
Thank you, Miguel. So we have time for 2 comments or questions from the audience.
Perhaps I could just comment, with this coming precision that we hope to have from future detectors, it really does.
Okay.
In order to do things like test GR, we need to have these waveforms from non-GR theories in order to make those comparisons with. And so that kind of tells you, there's your time frame. We have future detectors coming. They're going to come in 10 to 15 years. And on that time, we need to have full waveform models from non-GR models. And that's hard. Producing, particularly we need models that are fully consistent. We talked about numerical simulations before. We need to have ones that are well posed, that can have initial conditions. You can then evolve them and produce models that way. And there are less of those. So to do some of that precision science, there's a lot to be done on the modeling side as well.
Yeah, that's true. With all these alternate theories of gravity, you need a very well-posed system. I mean, it was extremely difficult. It took 40 years to be able to do a simulation of a collision of black holes with GR. And GR is a well-posed second-order theory. So if you have a very complicated theory, maybe even not second-order, fourth-order, then that's completely open. We don't even know how to start simulating those things. If it's a relatively close relative, say, a scalar tensor theory with just a simple scalar field, then maybe that we can do relatively simply. But if it's more complicated than that, I think it's going to take a long time just to understand how to do the simulations.
Okay. Miguel, how do you get information about the equation of state by observing the gravitational waves? It's not clear for me.
That's a good question, but I'm not an expert on neutron stars, so I don't know. I always work with black holes.
Maybe I can also comment on that, because at least when you're in the ring down, right, in this ring down phase, you can probably in the future discern the modes. And these modes, they are depending on the equation of state. I tried to show this briefly yesterday. From this one might be able to really derive something. I mean, we also have some universal relations for some of these modes, but if we have fixed certain quantities, we might then come back, so from the universal relation, go back to particular quantities and then learn about the equation of state from the gravitational waves.
Yeah, so that's right. We basically need to be able to look at the signal after the collision with good precision. And at the moment, we don't really have that. We see before the collision and we see the collision, and after that, detectors are just not good enough to tell us much, but we need to be able to see the aftermath of the collision with high precision. Then we should be able to extract things like that, normal modes of oscillation, and those things depend on the equation of state. So yeah.
And I think as well the tidal deformability. Sorry, yeah.
In the collision we had, we could learn quite a bit about neutron stars already. Let's say, try to obtain some upper limit on the mass within GR. So we have already also learned something about tidal deformability of neutron stars. And so I think if we have many new measurements of such events, then we will have a good chance to also from gravitational waves learn about neutron star equation of state.
Thank you, Jutta. Do you want to add something else, or?
No, but just to say, yeah, the tidal deformability is another way that you can measure things, because black holes are very specific deformability, whereas the neutron star one will depend upon its equation of state.
Yeah. Okay.
And
Thank you.
that part of the inspiral also appears in the current frequency range of the detectors. The problem with the ring down effectively is it's typically outside the range of the current detectors. It's too high a frequency.
Thank you very much. Very interesting. So our last question is this one. We are able to discriminate different types of compact objects, black holes, boson stars, and so on, according to its properties. I mean, gravitational waves, shadows, lensing, and others. Jutta?
I think we talked already a bit about the gravitational waves. So there, I would like to add one thing, namely the echoes. So if we have an object that has a horizon, and in contrast, an object that does not have a horizon, then there would probably echoes in the signal. So we would see some repeating gravitational waves and repeating signals after some time, which would not arise if we had a horizon, because without the horizon, we would have multiple scatterings. And this might be a signature that could tell us there is or there is no horizon. Otherwise, the shadow. At the moment, there are many objects that do show a picture, a shadow, very much like a black hole. For instance, the French group, the Paris group, they have very nicely modeled the shadow of a boson star. And even though there is no horizon, one does have this dark interior region. And then the disk around it. But one could be able, if one would have higher precision, to possibly discriminate than some higher scattering, higher, what are these things called? So the higher images of, let's say, the boundary of the shadow. So there we might have a chance also for some of these compact objects. There would be some very light features, so it wouldn't be completely dark in the center. We would have some rings or some bananas, some shapes. Also there, where for a black hole, it would be just black. So we might see something like that. So in such a case, we would be able to discriminate if we would have sufficient accuracy and yeah, better pictures. What else would we have? Yeah, maybe learn something about accretion disks, the quasi-periodic oscillations. They might be different for black holes and other compact objects. And I also think it's beside the gravitational waves that we have these instruments like the Event Horizon Telescope for the shadow, but also gravity. This will give us really big new insights into the electromagnetic range. So we probably will be able to discriminate a lot in the future with big, new, and now already running instruments.
Thank you, Jutta. Niels?
Yeah, again, I think I completely agree. I think with current gravitational wave detectors or things like the Event Horizon Telescope, we can tell that there are compact objects there. Our best guess is that they're the black holes of GR. Not when we talk about black holes, at least. And but we can't put good error bounds on most of these things, and we really are waiting for the next generation of detectors in order to do that. And maybe I'll just give an example. So in my own research, I mostly think about extreme mass ratio wind spirals. And you can detect these once you have the LISA detector. And one thing you can do there is you can measure the multiple moments of the compact object. And so we know if it's a Kerr black hole that once you specify the spin and the mass and the charge, that through the no-hair theorems, all the higher multiple moments are then set. So once you know those three, you know the quadrupole moment and so on. And yet once you can measure the gravitational waves from an emery, you can measure independently the quadrupole moment and see, you can measure the mass and the spin, and you can also independently measure the quadrupole moment and see if those all line up in the way that would be what you expect from a Kerr black hole or from some other object. And so if it's not a Kerr black hole, that would then become clear. And you're entering that kind of precision area because you can measure that quadrupole moment to about 1% accuracy. And so that gives you a strong test. But, as we were saying, you really have to wait for these new detectors to perform these high precision tests.
Thank you, Niels. Miguel?
Yeah, it's just what Niels and Jutta said. In principle, we should be able to discriminate because a lot of people have been working on this, and there's differences that you can have in the shadow and differences in the gravitational waves. We just don't have the detectors that are good enough today. We need to wait for the next generation detectors in the case of gravitational waves, and also to get much better images from the Event Horizon Telescope or something like that. At the moment, all these things are consistent with GR black holes. That's what they are. The precision is not great, but as far as we can tell, they are consistent. But if we push it further with newer generation of detectors, we should be able to see a difference. Also, I think it's the most interesting area to look at because if there's going to be a deviation from GR, one would expect it at high gravitational fields, are very strong gravitational fields, and that's around black holes. So if there is some deviation, we should see it there. And if we don't see it there, then I think we're going to be stuck with GR, right? There's nothing else we could do apart from quantum gravity, but that's it.
Thank you, Miguel. So if someone wants to add something to the discussion or some comments, questions, the participants? I cannot see the chat, so nobody?
So far, there is none.
Sorry? Okay. If not, we can conclude that we all believe in black holes. So thank you very much again. Celia,
Yes.
go ahead.
Also, we invite to all the speakers if they can join us by turning on your camera. I think there is Octavio, Jackson, Jürgen as well. Excellent.
I cannot turn on my camera.
Okay, Aline, you are there?
Yes, just waiting for all of the speakers to turn their cameras on.
I can't turn on my camera.
I think all the speakers,
I'll just Photoshop you.
Okay, excellent.
think Cesar was saying he couldn't turn on his camera for some reason.
I'm blocked.
Oh, let me check.
What?
Blocked by the host.
Let me help you.
Banned. Banned from the meeting.
Can you try now, Cesar?
Yes, I can.
Excellent.
you.
Thank you. You're
So
there.
please smile. Ready.
Excellent. Thank you very much. So, just by conclude the event. Okay, here we are. Okay, so on behalf of the organizers, I am very pleased to say thank you to all the participants, and also I would like to thank all the speakers. Thank you very much for joining us to this fourth edition of the Mesoamerican workshop on cosmology and gravitation, and hopefully we'll have the opportunity to see you in a couple of years. So we are planning to have our fifth edition for the 2022. Hopefully here physically in Mexico to enjoy together and have more discussion finally. So I wish you all the best, and please the box of questions if you want to communicate with the speakers, because that is the purpose of this event, to have these insights with all the participants, with all the speakers, to enjoy the collaborations and see future for this all this work that we are having in every corner of the earth. And thanks to this technology, we are capable to be connected as well. So I don't know if any of the organizers, Miguel, Elias, want to say some words.
Yeah, just I would like to thank to everybody, to the lecturers, the participants, all the people that joined us in this fourth edition of the workshop in these very, very hard times. So thank you all the participants, our lecturers, thank you. And we have to see you next year, maybe in 2 years, we don't know, depends on the some questions in here. So thanks a lot, everybody.
Yeah, I just want to add also thank you, Celia, and thank you, Elias, for organizing such a beautiful meeting. It was extremely interesting. Very nice 2 days. I do hope next time we can see each other in person and this pandemic is over. But I think that under the circumstances, you did extremely well organizing this event. Thank you very much, both of you.
Thank you, Miguel. Thank you.
Okay, so thank you very much, speakers, and well, see you soon.
Thank you.
Thanks,
Bye.
everyone.
Bye. Thanks for all.